Hello everyone, am I audible?
Yes, sir.
Okay.
Yes, sir.
So, good evening everyone. So, today is the third problem solving session for the course Introduction to Lasers. So, today what I am going to discuss is about the spectroscopic term symbol, which I did not discuss in the last week class. So, these are also generally known as only term symbol in atomic physics. Now, by definition, it is an abbreviated or short description of the total so it is an abbreviated or short description of the total It is an abbreviated or short description of total spin and orbital angular momentum quantum numbers of, the electron in a multi-electron atom. Okay, so these term symbols are basically based on LS coupling. Okay, now what is this LS coupling? LS coupling is basically uh, spin orbit coupling. So this is a spin orbit coupling. Now this LS coupling is uh, in atoms. So in atoms, the electron we have, those electrons have a certain spin and also has a certain orbital angular momentum. So let's denote that electron spin as Si and orbital angular momentum. Angular momentum Li. So now this electron spin will interact with themselves and it will combine to form a total spin angular momentum. And yes, Jaya. Jaya, is there any question or any doubt?
No, sir.
Okay. Okay, so the electron spin combine interact among themselves and they combine to form a total spin angular momentum capital S, and then the same thing happened with the orbital angular momentum Li, and then they create a total uh, orbital angular momentum L. Now the interaction between L and S give us LS coupling. Now this LS coupling has also another name. This is also known as Russell Saunders coupling. Okay, so this Russell and Saunders are two physicists, and this is known as LS coupling. Now, so the meaning of LS coupling, from LS coupling, what we get, that is J equal to L plus S, where L is summation Li and S is summation Si. So this J is known as total angular momentum. So here we are talking about spin angular momentum and orbital angular momentum. So basically in classical picture, what we assume is that there is the nucleus and then the electron is rotating around the nucleus. So this rotation will give you the orbital angular momentum, and then the electron is spinning around itself. So this is giving the spin angular momentum. So these two angular momentum are combining and giving us the total angular momentum. So this is a very crude example of that, but the physics behind this is complicated. So it's just for an analogy or something like that. Okay, so now so we have these three things, J, L and S. So from these three things we write 2S plus 1 L J. This is the term symbol. So now what now we have some value for this S, L and J. So so there is a process of calculating this value S, L and J, and after that we have a particular term symbol for a particular electronic state. Okay, but before that, in order to know the value of this S, L and J, there is a nomenclature for L also. So that will be given by a table L term. So for L equal to 0, the term will be used S. For L equal to 1, the term will be P. 1, 2, 3, 4, 5, 7. So here it will be S, P, D, F, G, H, I, K. So these are the name. So these term symbols are calculated for the outermost orbital. Okay. Now I will give a example. So suppose an atom or a ion or something has the outermost orbital has this kind of configuration d2, that is it can be anything like 4d2 or 5d2, anything like that. Okay, so this is the outermost electron cell. So d orbital means that so d orbital means that d orbital has basically 5 uh, boxes or place to accommodate electron. So d orbital can maximum hold 10 electron, and that can be arranged like this. The filling up of electron is basically done by this one, like first the electron will be in up spin, so this is basically d5. Then again if there is 7 electron, then that will be like first it will be filled with up spin, then it will start to fill with the opposite spin. So it will be like this. So this is d7. Now for example we are talking about d10, that is totally filled. So then if it is totally filled, then there is the 5 boxes. We will first fill it with up spin. These are the convention, basically up spin or down spin. Okay, so we can think of the spin can be in two direction. One is like clockwise, another is anti-clockwise. So here if you want to assume, you can assume that the up spin is basically referring to the anti-clockwise and down spin referring to the clockwise direction. It's just the convention. So if I am talking about d10, then it will be first filled with the up spin, then it will be filled with the down spin. Okay, so now here we are talking about d2. So for d2 it will be 1 2. So this is the d2. You cannot write down or draw the d2 by like this. Okay, or something like this and this. This is not possible. Okay, so now as you can see that the I am talking about d2, so 2 electrons in the d cell. So and now there is certain value or orbital angular momentum assigned to this cell, these boxes. So that is like +2 +1 0 -1 -2. So basically here you can see that there are 2 electrons. One has so L, that is the orbital angular momentum, L1 equal to 2, L2 equal to 1. So then capital L summation Li equal to 2 plus 1 3. And now these are the up spin and down spin. So in electron we think of that up spin corresponds to S equal to half plus up, and down spin corresponds to S equal to minus up. Now these two are up spin, so basically here the two electron has the same spin but in different orbital. Now so S will be half plus half, that is 1. Then so what we need to calculate, basically we need to calculate 2s plus 1 lj. These three things we need to calculate. So we already got the value of L here. Now we will need the value of S. Okay, so the value of S is 1, so 2s plus 1 will be 2 multiplied by 1 plus 1, that is going to be 3. Okay, so we got 2s plus 1 equal to 3 and L equal to 3. Now for L equal to 3, the term will be used F. So then 2s plus 1 L is going to be 3F. So for D2 orbital, this is the symbol. Now for this DN configuration, so D1 or D9 will give 2D, then D2 D8 will give 3F, then D3 D7 will give 4F, then D4 and D6 will give 5F, D5 will give 6S, and then D10 will give 1S. Okay, so this is how you calculate for a certain cell. Now I'll just write down the process one by one. So 1. First write the electronic configuration now consider only the valence electron, that is the electron present in the outermost shell. 3. Calculate the total orbital angular momentum value. 4. Calculate the total orbital angular momentum value, then calculate the total spin quantum number, that is S value. 5. Calculate 2s plus 1, which is known as spin multiplicity. 6. Calculate total angular momentum J value. Now 7 is known as the Hund's rule. So J, the value of J will be calculated like this: J equal to L minus S if subshell is less than half filled, and J equal to L plus S if subshell is more than half filled, and J equal to S if subshell half filled or fully filled. Now after that, the eighth step or the final step is to, as you have already, before this step you have already got the value of capital S, capital L and capital J. You can write down the term symbol 2s plus 1 L J. So these are the 8 steps to calculate the term symbol. Okay, so now there is a thing that is known as the spin multiplicity, 2s1, 2s plus 1. Okay, so now by spin multiplicity, what we want to say is that, for example, an electron has a spin half. Okay, so by definition, if we say spin half, we can say that it has either plus half or minus half. Okay, so that means that electron has a spin multiplicity 2. Now here s equal to half, so 2s plus 1 equal to 2 into half plus 1, that is 2. So this is giving the spin multiplicity of the electron. So now, for example, if we get the total spin angular momentum as capital 1, then there is a possibility that the total angular can be anything like plus 1, 0 or minus 1. So there are 3 possibilities. So 2s1, 2 into 1 plus 1, that is 3. So this is the spin multiplicity. This is saying that what is the number of possible outcome of the spin. And in this step, what is happening here, that the L and S are basically vector. Okay, L and S. So when these two, for example, to understand this, we can think of this in this way, like there are two vector L and S. Now if these two vector in the same direction, then for example these two vector in the same direction, then they will just add up. Now if there is two vector that are in different direction, then we will have only this much as the resultant. So by magnitude, this one implies L plus n and this one implies the L minus n or modulus. So this modulus means that it is either L minus S or it will be S minus L, any two of. Okay. Now I will give another example of P2 configuration. So before P2 configuration, I will just show how the steps are followed for D2. So as I have mentioned, then when we are talking about the D2, that means that the electrons are placed like this. In plus 2 there is one electron, and plus 1 there is one electron, and 0, minus 1 and minus 2 are empty. Now from that we have the orbital angular momentum of each electron is L1. For the first electron we have L1 equal to 2, and then for the second electron we have L2 equal to 1. So now the capital L, that is the summation of Li, is 2 plus 1, 3. Okay, so we get the value of L, then we get the value of S, that is the spin angular momentum, and for both of them it is up spin, so it is plus half, so it will be 1. So the spin multiplicity is 3. So when we are writing 2s plus 1 L, we have 3f. Now the value of here L plus S can be, so this is so this is less than half filled. by the half filled configuration is this one, D5, or full filled configuration is D10. So now for less than half filled configuration we have this rule, L minus S. So here L plus S value will be 2. So this will be 3F. Any doubt regarding this step? Okay, so now if there is no doubt, for example I will just write that S can accommodate 2 electron, P can accommodate 6 electrons, D can accommodate 10 electrons. Okay, so 2 electron means that there is one box, one up spin, one down spin. By 6, maximum 6 electron means there are 3 places: up spin, down spin, up spin, down spin, up spin, down spin. Okay, so this writing was wrong basically. So first up spin, up spin, up spin, then down spin, down spin, down spin. These are the 6 electrons. Then this is up, 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 down spin, down spin, down spin, down spin, down spin. This is how SP and D cell works. Now okay, so when we are talking about D, okay, so now one example is that S3 is not possible, but P3 and D3 are possible. So now P3 means this one, that is, this is half filled. Now D3 means this is less than half filled. So these are difference, so it depends on which cell we are talking about. Now the next example will be about the P2 configuration. So P2 configuration means that P2 means this one up, up. Here is nothing. Now plus 1, 0, minus 1. So 2 electron, there are 2 electron, L1 equal to plus 1, L2 equal to 0. So then capital L is 1, and then S1 is plus half, S2 is plus half, then capital S equal to 1. Now Now the spin multiplicity equal to 2s plus 1, that is 3. So the term symbol will be 3p. So this 3 comes from here, and this p is basically this. As I have mentioned here that the value for L equal to 1, that means the term symbol will be p. So this is 3p. Now we need to calculate j. So j will have values from L plus s to L minus s. So L plus s has a value of 2 to L minus s is 0. So the possible value for j is 2, 1 and 0. Now P2 is less than half filled. So then what is the rule? Yes, Dr. Sadhana. Yeah, the notes are already uploaded. So yeah, this note will be available to you by next Monday, I think, because I will upload today and then it will be sent to you guys. Okay. So there is no worry if you miss the previous part or you join late, or even if you miss the class, there is no problem, but it's better to join the class because then you can interact directly. The link will be provided by NPTEL team. I cannot share the link directly. Yeah. So P2 is less than half filled. So yeah. So if it is less than half filled, then we will follow this rule, L minus S. So L minus S means L minus, where capital L is 1, small l is 1. So less than half filled, so j will be L minus S, that will be 0. So then 2s plus 1 Lj, it will be 2s plus 1 is 3, L equal to 1, that means it will be p, then j equal to 0, 3p0. Now again we can calculate another, we can see another example, that is D8 configuration. So earlier I have discussed about the configuration D2, but here now I am going to discuss about the D8 configuration. So D8 means, first I will draw the boxes. Up spin. Now this is the D8 configuration. There are 8 electrons. Now so basically there are 8 electrons. So if I write it properly, then it will have L1 equal to 2, L2 equal to 1, L3 equal to 0, L4 equal to -1, L5 equal to -2, then L6 equal to +2, L7 equal to +1, L8 equal to 0. So these are the orbital angular momentum for different electrons. So there are 8 electrons, so there are 8 small l's. Now the capital L will be summation of Li, that will be 2 plus 1 plus 0 plus -1 plus -2 plus 2 plus 1 plus 0. This will give 3. Okay, now we got the value of L, then we need the value of S. So from here, okay, so for here calculating the S, we first need to write down the S1 equal to plus half, S2 equal to plus half, S3 equal to plus half, S4 equal to plus half, S5 equal to plus half, S6 equal to minus half, S7 equal to minus half, S8 equal to minus half. Yeah, so I am basically writing one after another electron. So first this one, then this one, then this one, then this one, then this one. But you can also write like S1 equal to plus half, S2 equal to minus half, then S3 equal to plus half, and then S4 equal to minus half. So it doesn't matter. So now as we have written the S for 8 electrons, so the capital S will be summation of Si, that is going to be so these two will cancel out, these two will cancel out, these two will cancel out, so there will be half plus half, it will be 1. So S equal to 1, so 2s plus 1, that is the spin multiplicity, will be 2 into 1, 1, that will be 3. Okay, now we have to calculate another thing, that is J. J equal to L plus S to L minus S. So here L is 3 and S is 1, so it will be 4 to L minus S, that is L minus S is 2. So it will be 4, 3, 2. Now here we can see that it is more than half filled. If it was half filled, then it will be like this is the half filled condition, but it is already more than half filled. So for more than half filled, what was the condition? L plus S, if half subcell is more than half filled. So this rule will be applied, and we will have J equal to 4. So the term symbol will be 2s plus 1 Lj will be 2s plus 1 is 3, L equal to 3, so that means uh, for 0 it is S, for L equal to 1 it is P, then it is D, and then it is F. Yes, so for L equal to 0 it is S, for L equal to 1 it is P, for L equal to 2 it is D, for L equal to 3 it is F. So it is F, then J equal to 4. So the spectroscopic term symbol will be 3F4. Okay, so this is how you calculate. Now till now I have only mentioned the outermost cell configuration, that is D8 or P2, or there was another thing, what is it? Yes, T2. Okay, now if I write electronic configuration, then how the problem should look like. Example, the question is calculate the spectroscopic term, sorry, symbol for the configuration 2p1 3p1 3d1. Okay, so this one is going to be very complicated, but okay, so you can see this, all of these are not totally filled. Okay, 2p1, p can hold basically 6 electron, but it has only one. Then this one only has only one electron, and then 3d has only one. Okay, so this all going to give a different value. So now for p, what we know is that there are 3 boxes, and then this is like this. And for d, okay, so for p, the L equal to 1. Okay, so for to start this problem, we'll first think about the 2p1 and 3p1. Okay, so now for this one the L equal to 1, this one, for this one the L equal to 1. So when you calculate the summation of L, there are 3 possible values: 2, 1, 0. Okay, it's like the same we have done for the L plus S to L minus S, because it was a vector sum. So here also, if this L and this L is added, then we will have 3 possible values. 2, that is the direction of these two total angular moment, total orbital angular momentum is the same direction, so we'll get 2, then there is 1, then there is 0. Now, and then there is the capital S, that will give us half plus half, that is 1. The spin multiplicity will be multiplicity is 2s plus 1, that is 3, and also there can be another s, that is half minus half is 0. So this is also the same like this one, that like we are adding a plus b, then there can be possibilities of a plus b to a minus b. So this one is giving 0. So now the spin multiplicity will be sorry for this adds multiplicity 2s plus 1 equal to 3, what is it, 2s plus 1 will be 1. That's the term symbol. So here the value of L equal to 2 1 0, so 0 is S, this one is P, this one is D. Okay, and then there is the value of 2s plus 1 is 1 and 3, so it will be 2s plus 1 Lj, sorry, we are not calculating j right now, so 2s plus 1 L, so 2s plus 1 is 3 and 1, so 3d 3p 3s, then 1d 1p 1s. Okay, so there are 6 states after coupling 2p1 and 2s1. Now these 6 states will couple with 3d1. Okay, so then we have to calculate the coupling between each of them. So now here I will calculate 3d and 3d, sorry, 3d1. So then for 3d, L equal to 2 and S equal to 1 as we have calculated earlier, and for 3d1 L equal to 2 and S equal to half. Okay, so this one is so from here we know that L equal to plus 2, so capital L equal to 2 and S1 equal to plus half, so capital S equal to half. Now we will just add the L and S separately. So here this is this 2 will be added and this 2 will be added. Okay, so now what we need to do is we need to add L and S. Okay, so L equal to 2 plus 2, so that will give us 2 plus 2 to 2 minus 2, it will be 4 3 2 1 0, and then there is S, that will be 1 plus half, it is 1 plus half to 1 minus half, that will give us 3 by 2 half. Okay, so from here this is S P D F G. Okay, and from here the 2s plus 1 will be 2 4, and from here it will be 2s, sorry, 2s plus 1 will be 2. So the possible term symbol due to coupling coupling 3D 3D1 is 4G 4F 4T 4P 4S, then 2G 2F 2D 2P 2S. So this is the only coupling that we have calculated, and after this coupling 3D 3D1 we get these states. Okay, so similarly we can calculate other coupling like 3P 3D1 3S 3D1 1D 3D1 1P 3D1 and 1S 3D1. So this is how the coupling works in the atomic physics, and we get different states. Like if you can remember, then in the last session I have discussed about a problem where we are seeing that there is the ground state, and then one state is suddenly splitted in two states. So this splitting is happening because of this coupling. So there is certain coupling in the states that is forcing that state to split into these two states. And if you check out the problems in any lecture book, you will see that the transition is shown between certain states. So these states are written in the terms of so basically by when we are given the spectroscopic term symbol, so it means that you can understand what was the electronic configuration of that particular state. So here we already know if it is D2 or D8, we know already what kind of spectroscopic term symbol we are supposed to see. So now I can just write down some spectroscopic term symbol for the ground state atoms, like hydrogen, it is 2s half, then helium, it is 7, 1 is 0, then lithium is again 2s half, beryllium is 1 is 0. So it depends on the outermost electron configuration. Then boron is having a different configuration, 2p half. So all these spectroscopic term symbol can be calculated from the configuration of the valence electron. Any doubt regarding this spectroscopic term symbol? Okay, so the next thing I'm going to talk about is the next thing is I'm going to talk about is Planck's law. So basically every physical body spontaneously and continuously emit electromagnetic radiation, and the spectral, so this thing can be written in terms of black body radiation like this: 2h nu cube by c square 1 by exponential of h nu kbt 1. Okay, so now this So now you may have seen this Planck's law in different in terms of different variable. So this is I am writing for your reference, just that this is the B nu. So nu here is the frequency. Now B lambda t is 2h c square by lambda to the power 5 exponential of hc by lambda kb t minus 1. Again in terms of omega t, we have h bar omega cube 4 pi cube c square exponential of h bar omega kb t minus 1. So these are the different forms of Planck's law in terms of different variable, and these variable are known as spectral variable lambda nu omega. Now from this Planck's law, there are two important law that can be derived. I will not show the derivation because the derivation is not important for now, but the laws are itself very important. One is Wien's law, another is Stefan's law. Okay, so Wien's law is Wien's law, or it is known as Wien's displacement law. So this law states that the black body radiation curve for different wavelength will peak at sorry peak at different wavelength that is inversely proportional to the temperature. So in mathematical term, lambda peak capital T equal to B, where B is equal to 2.897 into 10 to the power minus 3 mK. Okay, so basically this says that at different temperature the emitted electromagnetic wave has a different wavelength. So this comes from the Planck's radiation law. So another law is Stefan law or Stefan Boltzmann law. So so it describes the intensity of the thermal radiation emitted by matter in terms of the matter temperature. So the law actually mathematically describes that for an ideal emitter or black body, the total energy radiated per unit surface area per unit time is proportional to the fourth power of temperature. That is the m equal to sigma T to the power 4, where sigma is the Stefan Boltzmann constant whose value is 5.67 into 10 to the minus 8 watt meters Kelvin. Oh, now a very interesting application of this Wien's law is that as you can see that there is a temperature, then that temperature will correspond to a peak wavelength. Okay, so the one of the most interesting application in recent days, especially after the COVID, is that we have seen people use that thermal gun or thermal sensor, which basically looks like this. Okay, so now this thermal gun has a sensor that can actually measure the wavelength of the emitted radiation from our human body. So if you properly calculate the temperature and the temperature of our human body is, that is normal human body, that should be around 33 degree centigrade. Okay, so now if that thing is yeah, so corresponding to 33 degree centigrade, the wavelength that we can get from Wien's law is something around 9.5 micrometer, which is in the IR region. So if there is a IR sensor that can actually detect the IR wavelength, then that will be able to tell us the temperature of the human body. So using that technique, during the COVID time, people measure the temperature of the human body. But you can see that when you use the thermal gun, you see a laser is pointing towards our forehead or our chin or somewhat like that. So that laser has nothing to do with the temperature sensing or anything, because the temperature sensing is working in the IR region. That laser is just pointing towards the point where the temperature is being measured, but the principle of that the mechanism is solely based on the Wien's law that comes from the Planck's law. Okay, so if there is a thermal imaging of human body, then it will be around 7 to 14 micrometer range. Did you guys understand how a thermal sensor works? Okay, so now after the Planck's radiation law, there is another interesting thing that I will discuss, that is coherence. So coherence is totally related to the laser, and there are two types of coherence, that is, one is temporal coherence, another is spatial coherence. Okay, so now the first one is the temporal coherence. So by temporal coherence, it refers to the relative phase or the coherence of the two waves at two separate locations. So basically there is this electromagnetic wave, and after a certain distance the same electromagnetic wave might have different phase, relative phase. So this is known as the temporal coherence. So basically there will be a coherence length, that is LC. So this will be the LC. This temporal coherence also known as longitudinal coherence. So now if we assume two waves are at exactly in phase at the first location, then they will still be at least partially in phase at the second location up to this LC. So LC is the maximum length that the coherence is maintained in that particular laser. So in the laser people use in lab that has a few meters of coherence length, and in industry that might be larger, or it depends on the what kind of use they are doing, I mean the application they are doing. So it depends on the material and the internal structure of the laser. So but the coherence length can be changed. Now the formula for this LC is lambda square by delta lambda. So now this delta lambda is the difference in the wavelength, and lambda is the center wavelength. So LC is large only when delta lambda is much less than lambda. Okay, so now for an example, what is the temporal coherence length LC of a mercury vapor lamp? So the central wavelength is lambda naught, is given by 546.1 nanometer, and emission bandwidth is delta nu equal to 6 into 10 to the power 8 hertz. Okay, so now we know lambda equal to c by nu, or nu equal to c by lambda. So basically delta nu equal to minus c by lambda square delta lambda. So from there we can calculate the delta lambda is equal to lambda square delta nu by c. So then delta lambda equal to 546.1 into 10 to the minus 9, which is the wavelength, meter square into 6 into 10 to the power 8 second inverse, which is the emission bandwidth, then ultimately the speed of light 3 into 10 to the power 8 meter second inverse. So delta lambda is 5.96 into 10 to the minus 13 meter. So it gives that 5.96 into 10 to the minus 4 nm. So this is the emission bandwidth in terms of wavelength. Now the coherence length LC equal to lambda square by delta lambda. So lambda is 546.1 into 10 to the minus 9 meter whole square by 5.96 into 10 to the minus 13. This gives 0.5 meter. Okay, so emission for mercury vapor lamp is only 0.5 meter or 500 centimeter and 50 centimeters. So now we can do the same thing for a helium neon laser. So helium neon laser or He laser, which is the most used name here. So for helium neon laser, the operating at a wavelength of 632.8 nanometer with an emission with delta nu equal to 10 to the 6 hertz. So similarly here we will first calculate delta lambda. So this is the process of calculating delta lambda from given delta nu and lambda. So delta lambda equal to lambda square delta nu by c equal to so lambda equal to 632.8 nanometer. So this will 632.8 into 10 to the minus 9 meter whole square. Then delta nu is 10 to the 6 hertz. Then c is 3 into 10 to the power 8. then 1.33 into 10 to the power minus 15 meter, or 1.33 into 10 to the power minus 6 nanometer. Then the temporal coherence LC will be lambda square by delta lambda, which is 632.8 into 10 to the power minus 9 square by 1.33 into 10 to the power minus 15 meter. If you calculate this properly, we will have 301 meter. So here you can see that the coherence length of a typical helium neon laser is very high, that is 300 meter, which spans few normal size rooms. But at the same time, the mercury vapor lamp has only coherence length of up to 0.5 meter. That's why we say, or we claim that the laser has a very high coherence length. So this is one kind of coherence, that is the temporal coherence, or that is the coherence that actually preserved with time. So basically the electromagnetic wave is traveling here and the phase is preserved in this direction. Okay, not preserved in my drawing, but actually it is preserved. So for mercury vapor lamp, this direction is only 0.5 meter, but what helium neon laser, it is 301 meter. So the phase, relative phase, is preserved even after 300 meter. Now there is the second coherence. Is there any doubt regarding this coherence? Okay, so the next thing is the spatial coherence. So this time. Now the second coherence is spatial coherence. Now this coherence is also referred as transverse coherence. So this describes how far So by coherence we mean that the relative phase. Okay, so in temporal coherence we mean that after a certain distance the phase relation between the electromagnetic wave is preserved, and here it is the spatial coherence. So this is also known as lateral coherence. So this is denoted as LT. So by statement we can say that, more specifically we will ask by what distance LT can two points be separated in the transverse direction at the region of observation and still have interference effects from the source region over a specific lateral direction of the source. So if there is a source here and then the difference between these two part of the source is like this. So the general nature of any kind of beam is that it is expanding. So after a certain distance this beam will expand, and this is the LT and this is the R. Okay, so assume that the two sources are separated by a distance s in the transverse direction to the direction of observation and by a distance r from the point of observation. So here there is this source and we are observing the coherence at this point. Okay, so now this LT will be given r lambda by s. So here r is this particular distance, lambda is the wavelength, and s is the difference here. So you can see that this this spatial coherence is solely dependent on the lambda. So different wavelength has different spatial coherence property. So in temporal coherence it was like here the phase relative phase is preserved here, and these are also the relative phase is partially preserved here. So that is the limit of the temporal coherence, which we eventually find out that the temporal coherence for helium neon laser is 301 meter, and for mercury vapor lamp it is 0.5 meter. But here we are saying that at L so here we are saying that at this distance these two point will stop to show the interference effect, and we know that the basic criteria of exhibiting interference effect, that the two sources will interfere only when the two sources are coherent to each other. That is, there is a relative phase difference and that phase difference is constant. Only then we can see the interference. Now, but here we are saying that the two sources cease to show interference effect, and this LT is given as R lambda by S, or we can also write this as lambda by theta S, where theta S is R by S. Now there is an example. A laser produced plasma consisting of a 100 micrometer diameter ball radiates at a length of 10 nanometer So the question is, what is the spatial coherence resulting from light emitted from opposite side of the plasma at a distance of 0.5 meter? 0.5 meter. What the so now here the R is 0.5. Basically we are observing the source from this distance. So R is 0.5 meter, lambda is 10 nanometer, and S is 1000 micrometer. So the point of taking S as 100 micrometer is basically here we are thinking of two part of the source like this, and it is situated at a different distance S from each other, but here the laser we are thinking of a 100 micrometer diameter ball. So the ball is like this, and then by taking S equal to 100 micrometer we want to see that if these two points are coherent or not, two extreme point of the source. Okay, so now we will calculate LT equal to R lambda by S 0.5 1 into 10 to the minus. So this ours has 5 into 10 to the minus 5 meter. So at any location, so particularly for this plasma radiation, so at any location within 50 micrometer in any transverse direction from a specific point P, that is 0.5 meter from the source, the radiation will be incoherent, spatially incoherent. In order to visualize the spatial coherence, we can see that if there is a electromagnetic wave that has a wavefront like this, after a certain distance this wavefront will be distorted like this one. So this is the visualization of spatial incoherence. So in case of any uh, uh, lamp or something, we can see this kind of incoherence, but if you check this wavefront for laser, you will see that after a certain distance this thing is still like this, and this distance is very large. So basically these 2 points of the wavefront are here different, but for a laser it is still same. Any doubt regarding this coherence? So there is also another coherence that you will face in case of laser, that is spectral coherence. So I have said one is temporal, then spatial, then spectral. So the spectral coherence is that here the coherence is between different wavelength of light. For example, this is a particular wavelength of light, then this is another wavelength of light, and then this is another wavelength of light. So there has to be certain coherence between these, certain phase relation between these different wavelengths of light. Okay, so this thing will come in the part when you will be reading mode locking. So mode locking is a topic that will see how to that you will read when you will read about the how to generate short pulses. So there are two methods, one is Q switching and another is mode locking. And by short pulses I mean there will be, if there is a plane wave then that will be like this, but if there is a short pulses then there is nothing, and then there is certain pulse, and then there is again nothing, and then there is again a pulse. So these pulses are very short in time, and there is a difference between these two pulses. So these three coherence are maintained in a laser: temporal, spatial, and spectral coherence. That's why when we talk about coherent light sources, then we mostly talk about some kind of laser. Is there any doubt? So today I have discussed about the spectroscopic term symbol to properly distinguish and name the atomic state which comes from the LS coupling, so that the electronic states can be understood properly, and then the process of doing that finding that term symbol from LS coupling, The process of LS coupling is discussed, and then there is a bit of example for this LS coupling. Then there is the Planck's radiation law, and then there is this coherence part, which is actually very relevant for laser. So I'll try to show some more example on spectroscopic term symbol in the next class, and I will discuss some problem regarding the amplification part of laser in the next class. So is there any doubt regarding today's class or for any previous class? So if there is no doubt or any kind of feedback, then I'll end today's session, and thanks for joining today's class. We'll meet on next Friday at the same time. Thank you guys.